Good morning, fellow physics students. Today we're going to be doing just a brief introduction to special relativity by discussing how inertial frames of reference affect the passing of time and the size of objects. Now we know that in order to measure velocity, it has to be taken with respect to something else, and for simplicity, that something else is usually considered to be stationary. Since picture is worth 1,000 words, and 1,000 words would take a really long time and I'm lazy, let's explain it using an image. If we consider an object in motion and the stationary object to be a set of axes going in the x, y, and z directions, then all moving objects can be expressed in a way roughly identical to this. Meaning that if we consider a particle in an xyz plane moving at a constant velocity only along the x-axis, we then need a way to express that particle's displacement with respect to the coordinate planes. Fortunately for us, a massive nerd named Isaac Newton gave us these wonderful equations for such an occasion. These are called the Galilean transformation equations, with the prime values representing those in the moving frame. These equations rely on the assumption that time is absolute, meaning that it is the same in the moving frame as it is in the stationary frame. Not entirely accurate, but we'll get to that in a minute. And also the assumption that if Newton's laws are valid in a stationary frame, they also have to be valid in a moving frame that's going at a constant velocity. Anyway, a few hundred years later, this scientific scrub named Albert Einstein disagreed with these equations, primarily because they disproved equations derived by his good buddy James Maxwell, and being the good stand-up guy he is, Einstein did the only thing he could think of. He did a bunch of math and published a paper showing that Newton's work is only an approximation. He then also released two postulates that seemingly solved all of the problems plaguing physics at the time and effectively saved the world. His first one stated that the laws of physics are the same in all inertial frames, there's no way to measure absolute motion, and there's no perfect inertial frame. Essentially, his first postulate is just saying that physics works. The math works out, guys. I know, crazy? Who would have thought? The second one states that the speed of light in all inertial frames comes out to the same value of 299,792,458 meters per second. Or for people that don't have the time to push all those buttons on your calculator, 3 times 10 to the 8th meters per second. Going back to your boy Newton and his Galilean transformations, we now know that he wasn't entirely accurate, just really close. Einstein just had a gut feeling and just a bunch of pointless math to prove it, but a couple of other physicists, namely Albert Michelson and Edward Morley, managed to experimentally prove Einstein correct and find that the approximation that Newton proposed could be made an exact formula if the distance is shortened by a factor of 1 over the square root of 1 minus v squared over c squared, a term that we're going to call the relativistic factor gamma since it becomes very important later. Using this relativistic factor gamma, Hendrik Lorentz was able to specify the Galilean transformation equations to derive these equations to express the displacement in moving inertial frames. He then renamed them after himself to be called Lorentz transformations. One important thing to notice is that he also derived an equation that shows time itself is changing. For simplicity, the standard notation for these equations uses the relativistic factor gamma as well as the term beta representing v over c. The equations for the Lorentz transformations can then be simplified to this. Again, this is still assuming that motion is going purely in the positive x direction. Also note that gamma has to be greater than or equal to 1, because when the velocity is 0, meaning the moving frame is actually stationary, the equation for gamma goes to 1 over the square root of 1 minus 0, which is just 1. We also know that it is limited by the velocity being less than the speed of light to prevent you from dividing by 0 and breaking the universe, which gives it a vertical asymptote and allowing it to go to infinity. Just to show how this relativistic factor works, here's a quick graph showing you how it scales with increasing velocity. Looking at this, you can immediately notice a few things. First, you see this graph is done using v over c for one of the units on one axis. This is because the velocity has to be so high for any of this to matter that it's usually done as a percentage or a fraction of the speed of light. Second, the value stays pretty close to 1 until you start going really, really fast, about 60% of the speed of light, which is 180 million meters per second. In case you still don't get how this factor only becomes significant at extremely high velocities, consider this. Mercury orbits the Sun in 88 days at an average speed of 47.4 kilometers per second. Pretty dang fast when you also think about how the Earth orbits at a speed of around 30 kilometers per second. Such a high speed, yet the relativistic factor of that orbit is only 1.000000012. Also, the fastest spacecraft ever launched by humanity, NASA's Juno probe, was able to momentarily reach 73.9 kilometers per second as it entered orbit around Jupiter, meaning that the fastest speed of anything mankind has ever made had a relativistic factor of, drumroll please, 1.00000003. I would say it's safe to assume that both of these are about 1. Now that's out of the way, think back a minute to where we saw in the Lorentz transformations that time changed between the two inertial frames, since it was contracted by that gamma term as well. This is because of the difference between what is known as proper time and dilated time. Proper time, commonly denoted as T naught, is just the straight change in time between two events occurring at the same position in the same frame, such as the time between two camera flashes. Plugging that into the Lorentz transformation for time, you get this second formula. You can then notice that since the flashes occur at the same position, x2 minus x1 is 0, and t2 minus t1 is t naught. Therefore, this simplifies down to the equation for time dilation, gamma times t naught. This means that if humanity could design a perfect spaceship that could travel incredibly fast and launch it, a different amount of time would pass on the ship than on Earth. For example, if we put some guy named Bob in a spaceship that could go 80% of the speed of light, or 240 million meters per second, or about 537 million miles per hour, which is about 2.6 million football fields per second, for those who really don't understand how stuff is measured, and had him fly for what felt like a year before returning, Bob would say that 2 years had passed, but everyone on Earth would call him crazy, and say that he hadn't been gone that long, only about 14 and a half months. This effect is commonly described as moving clocks run slow. Now for the really crazy part. This same effect can be applied to the length of objects that travel. Now, before you burn me at the stake for being a witch and claiming that how fast something moves has a measurable effect on how big it is, just listen. Say we throw a meter stick on the impossibly fast spaceship with our homeboy Bob. If we call the proper length of the meter stick L naught and define it as the position of the right end minus the position of the left end, we can plug it into our Lorentz transformation equation, and also recognizing that they both occur at the same time, and after a little bit of fancy algebra and relating the proper length in each system, you find that the moving meter stick actually shrinks by a factor of gamma as well. Bob would actually see it as being 0.625 meters instead of its original length of 1 meter. Hey guys, thanks for watching. Hope you enjoyed it and maybe even learned a thing or two. Anyway, good luck and have an absolutely fantastic day.